is Shalina, and this is Lab 3, Black Holes and Orbits. So there are two parts of this lab. For part 1, the purpose is to analyze the movement of a star as it orbits around a black hole and use that to find net force and the mass of the black hole. For part 2, the purpose is to simulate a planet, its moon, and a spaceship and find a velocity for the spaceship in order to have it have a certain trajectory and not crash. This will all be done using GlowScript, and in order to simulate this, we will need to understand the concepts behind Newton's second law, gravitational force, momentum, and parallel and perpendicular forces. Most of these equations we will use are related to Newton's second law, which is just force equals mass times acceleration. We derived the velocity update and position update formulas in previous labs. This is very useful in helping get our point-by-point trajectory. Under that, the force of gravitation is the force felt on a system due to the mass of an object, and we are already given an equation for that. In the middle, I just showed how we get that force is equal to the change in momentum over time from Newton's second law. Finally, in the last part, I show how to get the parallel and perpendicular forces for F net and change in momentum. As we can see, F net equals F parallel plus F perp. For part 1, I took the starter code and alternated for my unique trajectory. The time between data points and the trajectory is 1 Earth day in seconds, so 24 hours times 60 minutes times 60 seconds will give us the proper amount of seconds in a day. To the right of that, I edited the code and marked on the left what formula I used to get each equation. On line 90, I was able to determine the mass of the black hole at each point in the trajectory by rearranging the gravitational force equation. On the last part, the arrows are just adjusted as needed to help us visualize F net, F parallel, and F perp in the situation and see how F perp will always go towards the system and F parallel is always tangent to the points. Here's a video of what is produced by my simulation. The star's orbit around the black hole is not circular, meaning there are different forces at each point in the trajectory, which we can visualize by how the arrows change direction. The magenta arrow is our F perp, the cyan arrow is F parallel, and the orange arrow is just the sum of these at each point, aka F net. Because of this principle, the mass is also different at each point, and we are able to take an average of that, which is about 1.53 times 10 to the 34 kilograms. Here, the system is our star because it is being influenced by the surroundings, which is solely due to the black hole's gravitational pull. In part 2 of this lab, I took the starter code and edited it in order to simulate a system where a moon is orbiting around a stationary planet and my spaceship is trying not to crash into either. I made the simulation time shorter than the default because it would have been running forever. I found the ship's velocity experimentally by just using trial and error and running the simulation until it didn't crash. For the net forces acting on the moon and spaceship, I calculated it all using the gravitational force formula to see the effective gravity of the planet and the moon on the ship and the planet and the ship on the moon. Finally, I was able to visualize the trajectory of the moon and ship separately by using the net force on the moon and on the ship and using position and velocity update formulas to calculate their point-by-point trajectory. Here are the results of my simulation, zoomed out and zoomed in. As you can see, the moon, which is in cyan, does its orbit around the planet, while the spaceship in magenta leaves the moon and continues the trajectory to avoid crashing. In the case of the spaceship, it is a system and the surroundings of the moon and the planet, assuming no other forces are involved in our perfect simulation. In the case of the moon, it is the system and its surroundings are the spaceship and the planet. Although it is not a perfect figure-8 trajectory, at least it didn't crash. Here are some possible errors in the experiment. Since the velocity was experimentally found, it is not precise, as it would take forever to find a velocity to produce a figure-8 trajectory. We also used a lot of approximations in this experiment, so it could be more precise, but it would just take so long to do. Also, this is just a simulation and not necessarily entirely representative of what we would see in real life, such as all the other forces and surroundings in play, and not just the ones we pick and choose like the black hole. So what does this mean in terms of momentum and net force? As we saw before, we can derive momentum and net force from the same equations, and they are equal. However, the information we get from them is not the same. I would say that the rate of change in momentum tells us what is happening mathematically right now, while net force tells us what we expect to happen due to the forces and how they add up. What if we want to predict the motion of the entire system? If we want to accomplish this, our computational model would have to be a lot more complex. For every single force, we would have to calculate how every single thing around it affects it. For example, to calculate the force of the moon, we'd have to find the force of the moon from the planet, from the star, and from the black hole. And then we do this for every single object in our system. We would have a million lines of code. I think there would be dominant interactions coming from the black hole and the star and the planet and the moon. And smaller interactions would be coming from like the star and the moon or the black hole and the planet, where those don't really affect it. Thanks for watching.